Okay, thank you for the opportunity to present this work at this conference. So I will be talking about the coupling between states in quantum dots and Majorana fermions in quantum wires. And this work was done in collaboration with Denis Revalier, Elena Klinovaja, and Daniel Loss, all at the University of Basel. Oh, okay. Okay, that's better. The existence of Majorana fermions in quantum wires was kind of theoretically proposed some years ago in a series of papers, and it turns out kind of the necessary ingredients for realizing Majorana fermions in quantum wires is a spin-orbit interaction, magnetic field, and induced superconductivity. So the kind of picture one likes to have in mind is you have a quantum wire like this with some spin-orbit interaction in it, and a Zeeman field, a magnetic field that's applied everywhere. So there's some Zeeman field induced within the wire, and the wire is typically in contact with an S-wave superconductor, so there's a proximity-induced superconductivity. And the criterion to be in a topological phase is that the square of the Zeeman splitting has to be greater than the square of the proximity-induced superconductivity plus the square of the chemical potential. And when that is true, you have Majorana fermion bound states at the edges of the topological section region with a non-topological region. And these are zero energy bound states. Shortly after the prediction of Majorana fermions in quantum wires, there were quite a few experiments done to detect them using conductance measurements. So in these experiments, roughly a nanowire was deposited on top of a superconductor, and a magnetic field was applied to the system, and then the conductance was measured through the quantum wire. So, okay, in all these experiments, basically you see when the magnetic field is zero, you have the gap due to the superconductor, so you have no conductance at zero energy. But as you increase the magnetic field, you transition from the non-topological phase to the topological phase, and therefore you get a Majorana existing at the boundary, and therefore you have a zero bias conductance. And this is basically what all these experiments observed. So in more recent experiments, the setup changed slightly. And in this case, instead of depositing the quantum wire directly on top of the superconductor, they actually put an aluminum shell on top of the quantum wire, and this allowed and this induces proximity induces superconductivity by proximity. And in addition to that, they had a quantum dot that they could also play with at the end of the topological section of the wire. So here is basically the topological section, and here is some gate-defined quantum dot. And so you can see that this experiment has some nice results. So they have a hard gap, and they see a zero bias peak. And what's also nice is that they have this, so maybe this quantum dot can be good to actually measure Majorana fermions, but in addition, it could be also be helpful for quantum computation. So let me just give a short introduction to using Majoranas as qubits. So the basic ingredients for using Majoranas as qubits is one needs 4 Majorana fermions, and one needs to fix the parity fix the parity of your states. So, okay, choosing, let's say, odd parity, you define the zero energy, the zero state of your Majorana qubit as the, let's say, left. Okay, so there's 2 topological superconductors, and when the left topological superconductor, the Majoranas in the left topological superconductor are occupied, it's in the so-called zero state, and when the Majorana fermions on the right topological superconductor are occupied, then it's in the 1 state. And okay, this is nice for storing information, but unfortunately, one cannot do universal quantum computation that's topologically protected using Majorana qubits. So there's lots of solutions to kind of facilitate the additional gates, quantum gates that one needs to perform in order to facilitate a universal quantum computation. And one solution we gave, or one possible way to facilitate these additional gates is by including a quantum dot. So this was an idea that we had last year, and essentially one takes, roughly speaking, a Majorana qubit that's composed of two topological superconductors, one on the left and one on the right, and coupling it to a quantum dot. So the topological superconductors are described roughly just by this equation. So there's can be possibly some overlap of the Majorana fermions in each individual topological superconductor. And the quantum dot is defined by two, in principle, non-degenerate energy levels and an on-site interaction given by this. And then additionally, there is a tunnel coupling between your Majorana fermions and the states on your quantum dot. So what one can show is by applying a Schrieffer-Wolff transformation to this tunneling Hamiltonian, you obtain so by applying a Schrieffer-Wolff transformation and assuming that the topological superconductors are very, very long, then you obtain a rather simplified Hamiltonian that couples the spin qubit and the topological qubit. So sigma 1 basically takes you from the up state to the down state in the spin qubit, and eta 1 takes you from, let's say, the 0 state and the 1 state in the topological qubit. And what one can notice about this is because you have a tensor product between sigma 1 and eta 1, and this is in fact an entangling qubit. And because it's an entangling qubit, you can perform, well, okay. So with this Hamiltonian, you can perform some single qubit operations and obtain this Hamiltonian. And by allowing the Majorana fermion to, the Majorana qubit to interact with the quantum dot for some specified amount of time, one obtains a C0 gate. And by applying the C0 gate in a particular way, so by applying it once and then changing the control and target qubits, and then applying it again, one can actually generate a swap gate. What a swap gate does essentially is transfer the quantum information from the spin qubit to the Majorana qubit coherently. So the idea is essentially one can perform some topologically protected operations on the Majorana fermion qubit, and then to facilitate the operations that are not there for universal quantum computation, one can swap the information onto the spin qubit, perform the necessary quantum operation there, and then swap it back into the topological qubit. So basically, I guess it would depend on this T changes, and so basically we assume that like the Majoranas were coupled equally to up and down. But in general, okay, if you have different T's, it's a strong assumption, yeah. And that it's a strong assumption, it gives you the simplest result. But you can also get a much more complicated matrix, some general, roughly speaking, exchange, kind of pseudo-exchange interaction between the qubits with lots of different entries. And you can still get entangling gates, definitely. It just, the kind of recipe to get a swap gate, it becomes a little bit more complicated. I suppose so, yeah. So then we went one step further and kind of developed a scalable network of these kind of hybrid spin Majorana qubits. So the atomic element of such a network is essentially these kind of T-shapes. And these T-shapes are basically a kind of spin hybrid qubit. So this red part is the topological section, and this blue is the spin qubit, and this gray part is the non-topological section. The point is, for each of these individual atomic units, one can perform a Hadamard gate and a pi/8 gate. So all the kind of necessary single qubit operations are there for each individual qubit. And the new ingredient that we add to this kind of scalable network is some long-range coupling. So here we have some kind of long-range bridge that, whereby the spin qubits directly, there's some exchange interaction between the spin qubits in different kind of atomic cells. And what one can show is that by letting the two spin qubits couple, you can actually facilitate a C0 gate between the Majorana fermion qubits in adjacent atomic cells. And in this way, you can kind of generate universal quantum computation in a scalable network. So kind of an important thing about this scalable network, essential to us, is the coupling of Majorana fermions to quantum dots. And also we had a nice talk yesterday from Stefan, where he also utilized quantum dots coupled to Majorana fermions. So kind of the question that we wanted to ask is, what is the coupling between quantum dots and Majorana fermions? So the goal is basically to determine the spin-dependent coupling between the quantum dot states and Majorana fermion states in a quantum wire. Specifically, there's some tunneling Hamiltonian that's written down like this, and what precisely is T sigma? So the way that we figure it out is we do an analytic calculation, which makes some assumptions, and then this is used to inform some type binding results, which I think which is a setup that's pretty close to kind of experimentally realizable systems. So the way we're going to do it is we're going to calculate the wave functions of the quantum dot and the Majorana fermion analytically, and then we'll calculate the overlap, and this should give you exactly the tunneling between the quantum dot states and the Majorana fermion. And then once we've done it for one Majorana fermion, we'll consider the effect of coupling the quantum dot to two Majorana fermions. And then we'll compare it to the some type binding model analytics numerics that we did. So this is the basic setup that we have in mind. We have a spin-orbit interaction and a Zeeman field applied over the length of the wire, of the quantum wire. Here, this red part is in the topological sector, and this gray part is in the non-topological sector, and this quantum dot is, let's say, gate-defined within the non-topological sector. And in general, we consider the Majorana to be a distance L away from the quantum dot. So let's get started calculating the Majorana fermion wave function. So the Hamiltonian that we take has all the basic ingredients in it. So it has some kinetic term, a spin orbit term, induced proximity-induced superconductivity, and a Zeeman splitting. And these can be written down like this in some basis. And we tune the between the topological and the non-topological regime by changing mu. So on the topological side, it's mu sub t, and on the non-topological side, it's mu sub n. So in the strong spin orbit regime, this can be solved exactly. So in this solution, we assume that the chemical potential on the topological side is equal to 0, and on the non-topological side, it's something finite to drive it into the non-topological regime. And what one can see is that there's basically this is the solution, and on the topological you can show that so to satisfy continuity and differentiability, you get this solution, and what you find is that this wave this component on the topological side basically has two decay lengths given by the topological gap and the superconducting gap, and and two wave vectors. One is 0, so it's constant in space. It has no oscillations, and one that has oscillations with 2 KSO. So when you plot the square of the wave function on the topological side, it kind of looks like this. And on the non-topological side, you get one decay length given by the superconducting gap, and the wave vector has only one oscillation rate given by twice the spin orbit wave vector. And so when you plot the square of the wave function on the non-topological side, it just kind of looks constant. So now we calculate the quantum dot, the wave function of the quantum dot. And so to calculate the quantum dot, we make some simplifying assumptions. We consider a fully depleted dot, so no superconducting correlations. We consider a parabolic confinement, and we look in two limits. So one limit is when the size of the dot, L, is much, much smaller than the spin orbit length, and when the size of the dot is much, much larger than the spin orbit length. And in the case when the size of the dot is much, much smaller, the Zeeman energy dominates, and one can neglect the spin orbit interaction. And in the latter case, the Zeeman splitting is suppressed exponentially. So essentially, the levels, the spin up and spin down levels, are degenerate. So here are the solutions. Roughly, it's a Gaussian solution with a spinner that has no oscillations, and the energy levels for the small dot have a large Zeeman splitting, and for the large dot, one has also a Gaussian distribution, a Gaussian profile, but additionally has some oscillations with an oscillation rate given by the spin orbit wave vector. And these states have the spin up and spin down states are degenerate. So now we would like to calculate the overlap. So this is essentially given by just the average. We would like to calculate the spin-dependent coupling, which is essentially given by the overlap of the wave functions, just here. Here T naught is a phenomenological constant out in front, which depends on how you kind of, I guess in experiment it kind of depends on how you connect the Majorana fermion with the quantum dot. And when, in the case of the small dot, you get some easy analytic results given by this, which are plot here. And the salient things to notice about this is that, okay, the spin up and spin down, okay, they have equal weights of imaginary and real parts, and they oscillate with 2 times KSO as a function of the distance between the Majorana fermion and the quantum dot. Next, notice that they decay at a rate given by the superconducting gap. And finally, they differ by in phase by pi over 2. So okay, you can also do the calculation for a large, when the quantum dot is large compared with the spin orbit length. And roughly speaking, you get a similar result, but the oscillation rate is half as much. And what's important, I guess, what's interesting about this is that the tunneling can kind of be tuned. So depending on the distance between the Majorana fermion and the quantum dot, you get a different ratio of the magnitude between the up and down spins. So let's say if the distance between the Majorana fermion and the dot is at this value, then actually you have kind of spin polarized. You have the Majorana fermion only couples to one, let's say the down spin state on the quantum dot. Whereas if you are, let's say at this point, then the coupling between the up and down states in the Majorana fermion are equal in magnitude. So that's the story for one Majorana fermion. Now we would like to consider 2 Majorana fermions and see what happens. We consider the coupling of 2 Majorana fermions to the quantum dot. So okay, it's essentially the same tunneling Hamiltonian, except you have an additional index coupling the to, let's say, the left and the right Majorana fermions. And you can parameterize the left and right Majorana fermions into a complex fermion given by F, with this given by F, and its F is defined by this quantity. And you can kind of play the same game that we played with the qubit, before, and what you find is that you get some effective Hamiltonian that looks like this. And what this effective Hamiltonian tells you is that there's actually an effective Zeeman splitting of the levels on the dot. And this effective Zeeman splitting of the levels on the dot actually depends on the occupancy of this fermion that's formed at the junction of these two topological states. So that is to say, when the fermion state is occupied, the dot states feel an effective magnetic field, effective Zeeman splitting given by, let's say, B+. And when the state is empty, then the states on the dot feel an effective Zeeman splitting given by B-. So, okay, we can go using basically calculating the tunneling overlaps again, and then you can show that the magnetic field felt by the states on the quantum dot are given by this. You can plot them, and essentially what you notice is that the 1 and 2 components of the magnetic field, okay, they're out of phase. They oscillate at a rate of 4 kso, and they're out of phase by pi/2. And you see that the magnetic field component along the direction 3 just decays exponentially and does not oscillate. And furthermore, what you notice is that the only component that depends on the occupancy of the state formed from the Majorana fermions is along the 1 direction. So you have an overall plus minus depending on if the magnetic field along 1 direction changes sign depending on whether the state at the junction of the two Majorana fermions is occupied or unoccupied. So, okay, this is in the small dot regime. This is what you find, and you can also do the same calculation in the large dot regime, and you get roughly the same results. Okay, so that's basically, so yeah, there's an effective Zeeman field can maybe be used to detect Majorana fermions, or the state of the Majorana fermi candidate. So we also did a type binding model, and in the type binding model we took basically a quantum wire, and part of the quantum wire has proximity-induced superconductivity, and the other part of the wire has no superconductivity, and we defined a quantum dot on that side of the wire. So this part is the topological part, and this part is the non-topological part. And there's a Zeeman field throughout the entire wire. So you can go through and calculate the wave functions in such a system, and you see basically your quantum dot wave functions look like this, and your Majorana fermions live at the edges of the topological region. And here is the energy spectrum. So in the red, you have the Majorana fermions, which sit nicely at 0 energy, so you know the size of your topological set region is long enough. And the up and down states on your quantum dot are roughly degenerate. So you know you're in the regime when the size of the dot is, let's say, larger than the spin-orbit interaction. And basically, the energy of the dot when the Majorana fermion is very far away from the dot is given by epsilon naught, and as it gets closer and closer, they start to couple together, and the energy of two degenerate levels with the 0 energy Majorana is given by this, and from this quantity one can calculate the magnitude of the spin dependent coupling. How much time do I have? A few minutes? Okay. I'm almost done. So that's basically what we did. So we changed the distance between the Majorana fermion and the quantum dot. And, okay, similar to the analytics, we see oscillations of the spin up and spin down tunnelings shifted by roughly pi/2 with respect to each other. And they have oscillations given by roughly the spin over length over 2. So then we considered a Majorana fermion, so 2 Majorana fermions coupled with the quantum dot, and you can see that the local density of states is roughly the same, except you have 2 additional Majorana fermion states, and likewise the energy spectrum is the same, except you have 2 additional Majorana fermion states, also at 0 energy. and then we calculated the spin on the dot. So we moved the Majorana fermions equidistantly away from the quantum dot, and then we calculated the total spin on the dot, and we found that along the y-axis, the spin along the y and the x-axis, the spin oscillated with a periodicity of the spin over length over 2, and the spins were out of phase with each other by approximately pi over 2 as well. And this is consistent with what we saw in the analytics. So just maybe some concluding remarks about what we saw. So the spin-dependent tunneling depends on the distance between Majorana fermions and quantum dots. So okay, this may be a good thing. This could in principle tell you if you had the ability to fine-tune the position of the two, then you could actually fine-tune the tunneling between the quantum dots, or the quantum dot and the Majorana fermion, to whatever ratio of up and down, T up and T down you like. But the bad is that, okay, if you don't have such fine precision, or you cannot move your quantum dot or Majorana fermion, then you may be unlucky in your position. You may get a ratio of T up to T down that is not something that is useful for your experiment or theory or whatever you like. And it could be, in general, a source of error for readout and operations of your qubit. And finally, that the spin or the effective magnetic field on the quantum dot can be used as a detector for the Majorana fermion qubit. And just a brief outlook of things that we're also interested in. So we'd like to kind of explore the same system of, let's say, of a Majorana fermions coupled to a quantum dot, but instead of nanowires, looking at, let's say, atomic chains. And also, we would be interested in kind of transport measurements in such a system and seeing what the position dependence of the position dependence between the Majorana fermion and the quantum dot are in, let's say, differential conductance or so. Thank you for your attention.